Good evening to one and all. Only few members are joined. We'll wait 2 more minutes and we'll start the session. Thank you.
Okay. Welcome back, everyone. We are now ready to begin session one of day 5 of our FDP program on the revolution of large language models in AI. Myself, Dr. Anusha Ampavati, coordinator of this FDP. So I wanted to give you some general information about today's FDP program. Today is the same earlier. We have the two sessions we have. The first one is LLMs for generating novel molecules with GANs by Honorable guest and speaker Kaushik Bhargat Sivangi. And the session 2 will be on topic of LLM application document query, how the query and everything by Shaurya Kushal Garu. So now I want to give the mic to Ms. Shweta Chikati to introduce our honorable guest of session 1. Thank you. Over to you, Shweta ma'am.
Okay, ma'am, thank you. Good evening, ladies and gentlemen. I'm Sweta Chikati, serving as an assistant professor in the Department of Artificial Intelligence at Vidyajyoti Institute of Technology. It is great pleasure and privilege for me to welcome and introduce our distinguished guest, Kaushik Bhargav Sivangi sir. Kaushik Bhargav Sivangi sir, a distinguished research associate at BioAM Lab, University of Glasgow. With over 4 years of experience in interdisciplinary academic research, Kaushik Bhargav Sivangi sir has made significant contribution across a range of cutting edge fields, including human motion analysis, privacy preserving deep learning, sensor based AI applications, bioinformatics, neural cryptanalysis, and uncertainty estimation in deep learning models. His research is centered on developing innovative, scalable AI driven solutions to tackle pressing real world challenges at the intersection of artificial intelligence and health informatics, pushing the boundaries of what AI can achieve in healthcare and beyond. I humbly request Kaushik Bhargav Sivangi sir to take the proceedings of this session. Over to Kaushik Bhargav Sivangi sir. Thank you.
Thank you, Shweta madam. Can you all hear me?
Yes, sir.
Okay, so I'll just share my presentation. So can everyone see the slide?
Yes, thank you.
Um, okay, cool. So this is Kaushik, and
Sir,
thank you, Shweta madam.
Sir, can you please
Yeah,
switch on your video, sir?
Oh, sorry. Just a second.
Thank you, sir.
Am I
Thank you.
visible?
Yes, hi.
Okay, perfect. So yeah, welcome everyone and good afternoon. I guess it's good evening in India. So myself, I'm Kaushik Bhargav. So I'm currently working as a research associate at University of Glasgow in BioAM Lab. So today my topic is about providing some sense of overview of how large language models are being used in drug discovery, which translates to de novo drug discovery. Yeah, so let's talk about the motivation. So have you ever wondered as to what the journey behind a simple medicine or a simple tablet which you usually take, like say paracetamol or Crocin or some tablet that you might take for a headache, cold, or something like that, how long it usually takes to develop and how much does it cost? So what seems like a quick fix for your pain actually has a long, complex backstory, and it usually spans decades of research and usually costs around billions of dollars. So, for example, the average time to develop a single drug is around close to 10 to 15 years. And this is by no means an exaggeration. And it's not just about time, and it's also a massive financial investment. Bringing one successful drug to market costs more than $2.5 billion. And this is with most of the cost going into research, development, and testing. And this is not the entire story, but even with this enormous amount of investment, the thing is that only less than 10% of the drug candidates enter the clinical trials, uh, and they actually succeed. So this entire process of drug discovery is filled with challenges, but the rewards, obviously, you save some lives in the end. And I just want to explain the stages, three key or high-level stages of drug discovery. So we can break the process traditionally into three main stages. And the first stage is all about identifying the disease and what's the target. And the second stage focuses on designing and developing potential treatments aimed at this target. And finally, in the third stage, these treatments are rigorously tested in clinical trials, which involves animal testing and human testing. And this is just used to assess the safety and effectiveness of the drug. So each phase, I mean, the challenges for each phase is that it's incredibly time consuming and it's obviously resource intensive. And primarily this stems from the fact that the biological systems are very complex and the extensive research and validation needed at every step adds only to the difficulty. So this slow nature of drug discovery often hinders the timely introduction of life-saving therapies that could significantly improve or extend human lives. So addressing these challenges is where technologies like large language models can play a transformative role. So yeah, uh, let's just discuss each step as where can LLM fit into this scenario. So in the first stage of understanding the disease mechanism, that is identifying the target, uh, LLMs can significantly enhance our ability to understand disease mechanisms. They can process vast amounts of data, literature, pattern data, and explore biological pathways and identify potential drugs or therapeutic targets, for instance. And functional genomics analysis can be conducted to pinpoint genes with desirable mechanisms of action. This usually helps researchers identify strong drug candidates against a target. And additionally, by analyzing in vivo and in vitro experimental results, which just means that out of body and inside the body experiments, LLMs can infer novel insights into biochemistry and pharmacology and uncovering principles that were previously unknown. So the drug discovery development, the second phase, LLMs help automate complex chemistry experiments such as predicting chemical reactions or chemical synthesis. And they also provide interactive platforms for molecule editing and generation, which usually helps the experts in discovering new compounds that meet certain desired characteristics. And in advanced uh, therapies, for instance, like gene therapies, LLMs can play a crucial role in designing the AAV vectors. And by summarizing scientific literature and analyzing genomic sequences, LLMs can predict the most effective vector sequences for safe and efficient delivery. And coming to the clinical trials, obviously, so after you discover a drug, you want to know if it is actually working or not. So LLMs streamline the process of matching patients to trials by interpreting their profiles alongside trial requirements and things like that. And they can also assist in trial design by analyzing historical data, helping to create more effective trial protocols. And existing research also suggests that LLMs might predict trial outcomes for which we could save some significant time and resources by focusing on the most promising candidates. So for this presentation for today, we'll be focusing on some of the case studies in drug discovery. Yeah, so let me just elaborate the three stages which we discussed previously. That was more of a high level view, but if we break it down further, we have an entirety of 6 key steps in the drug discovery. So, and discovering drug is not something you can just achieve in, say, a couple of months or a couple of years. So even after years of work, there is no certainty that the drug will make it to the market. And sometimes a drug that works well in animal trials might fail in human trials. So this uncertainty means a lot of time and resources are spent on molecules that may never even become viable at any later point of time, which is just waste of resources and time. So just to explain the 6 key steps of the drug discovery. So first is the target identification. So before you discover a drug, what are you discovering the drug for? So you start with the disease. For example, you might suspect a protein is probable because of the disease. So identifying this target protein is the first step. And the next step is the target validation. So after identifying potential target proteins, or it can be genes as well, we need to validate them. So if you shortlist 5 proteins, only one might actually be involved in the disease. You also assess the druggability, which means that if a target can bind effectively with any given drug. So without proper binding, it's just a waste of time and the drug won't reduce or stop the disease. And the next key step is lead identification. So you screen a library of compounds to find a potential lead compound that binds successfully to the validated target. And if it binds, you just proceed with it. And the next step is the lead optimization. So in the lead optimization, once you have a lead compound which you have identified in the previous step, you just try to refine its structure to optimize properties like efficacy, safety, and stability. And this just ensures that the compound performs as intended. And next comes the animal trials. So we just test the drug in living organisms to observe its effects, and it just helps us to understand how the drug behaves in a biological system. And then comes the human trials. So finally, we just test the drug in small doses on few volunteers uh, to assess its safety and efficacy. So since we don't yet know how it will react in humans, multiple trials are usually conducted before it can be approved for the general public. So in this entire context, where do LLMs fit in? So the first step in drug discovery was, as we discussed, was identifying targets. So proteins or pathways linked to a specific disease. So this process can be slow due to sheer volume of data in scientific literature and patents. So LLMs, for instance, I can just put an example as a gene farmer LLM. In general, any specific biospecific LLM can automate this entire process by mining literature and genomic data to identify disease-associated targets. And they also map biological pathways to potential therapeutic targets. And this just drastically reduces the time and effort needed. And by accelerating this target identification, LLMs allow the experts/researchers to focus on the most promising leads early in the entire drug discovery pipeline. So checking how the LLMs fit at each step, let's discuss in the first case of target validation. So once a target is identified, the next step is validation. So ensuring the target is relevant and druggable. LLMs assist by analyzing experimental data and predicting characteristics like binding affinity and other affinity scores. So, for example, an LLM can evaluate a gene-disease interaction or suggest hypotheses to test in the lab, thus just making the validation process more efficient and precise in nature. And in the next step of lead identification, which comes after identifying a valid target. The next step is finding the molecules that can interact with them. So LLMs help generate novel molecules, often using de novo design tailor to specific properties like binding affinity. And additionally, they can perform retrosynthetic planning to suggest efficient synthesis pathways and predict molecular properties like ADMET, which basically means absorption, distribution, and what was the other? Absorption, distribution, metabolism. E is for the excretion, and T is the toxicity profile. So once you take a drug, how well it is absorbed in the system, how well it is distributed in the system, how well the metabolic system of you accepts the given drug, and the E stands for excretion, how well the drug exits your body, and the T stands for toxicity, which says how toxic is the drug for you. And the next step is lead validation and optimization. So in this, it just involves refining molecules to enhance their properties, such as increasing efficacy or reducing toxicity. And LLMs use predictive modeling to simulate protein ligand interactions and suggest some molecular adjustments. We'll see an example later in the presentation. And coming to the final part, which is the animal and human trials. So obviously, it says human trials are one of the most complex and expensive steps in drug discovery. And the way LLMs simplify this process is by matching patients to trials, designing protocols, and even predicting trial outcomes based on some sort of historical data which you provided. So by automating the documentation and result analysis, LLMs reduce administrative burdens, allowing researchers to focus on improving trial success rates. So since the entire concept of drug discovery is a bit niche topic and it has pretty niche audience, I just took a bit of liberty to explain what LLMs are in general. So what are LLMs? Sorry. Yeah, sorry. So what are LLMs? So LLM stands for large language models, or sometimes they're referred to as large pre-trained language models. And these are, sorry. So LLMs are just complex deep learning models designed to mimic human language, and they are trained on massive data sets like books, articles, scientific papers, or any textual matter which you can just find. And it just allows the model to understand, generate, and analyze text for various tasks. So why are they called large? The large in this refers and stems from three main factors. One is the large data sets which it is trained on, the large architectures, it's the large model slash architecture of the LLM, and large computational needs. So coming to the data sets, LLMs are trained on like billions and billions of text examples. For instance, GPT-3 was trained on a data set encompassing a significant portion of the internet. And coming to the large architectures, the size also comes from the number of parameters. So which are the tunable parts of the model. So for example, again, GPT-3 has 175 billion parameters. And yeah, and if you take any in general model, which you might use to train your everyday data sets, it might be just like 100 million or 200 to 300 million, but never a billion. But let imagine just 175 billion. And the computational needs, training LLMs requires vast computational power. It can take weeks on thousands of GPUs to train a single model, which is a sad bit, which that is that it just makes it accessible only to organizations with substantial resources. So let's discuss a bit about the building blocks of large language models. So the entire story started with the attention mechanism, which was initially proposed in the year 2014. So there are a lot types of attention mechanisms. So the very first prime attention mechanism was referred to as the Bahdanau attention, named after its author. So this was originally developed for machine translation, which is just a sequence to sequence model. So in a single line, what it does is it allows the model to search for parts of a source sentence that are relevant in predicting the target word. That is, we assign some weight to each word of the sentence to know how much attention the model should pay to each word. And the network just learns the context. So for example, if we take, I hope everyone knows what an RNN is. So if we just have an RNN network, which is a bidirectional, let's take a bidirectional example from the original paper itself. So you just pass on your input sequence to a forward propagating RNN and as well as a backward propagating RNN, and you just take those outputs, concatenate them together, and you get some hidden state. Let's call it as a HT. And along with that current hidden state, you also pass on the output of the previous time step, which you can see as ST minus 1. So you just pass them to another neural network and you get some values out of it. And when you apply softmax on it, you get the attention weights, which corresponds to each hidden state of the input sequence. And after you concatenate all these attention weights together, what you get is called as a context vector. And yeah, this just provides the entire context of the current sentence in the current given state of the output prediction. So I'll just provide a quick visualization. So usually these attention weights are between zeros and ones, so such that you have a probabilistic distribution. And for example, if you have a translation task, let's say there is an English sentence which you're translating to some other language, it can be French, something like that. So if you see the top word, and its correspondence is with the first word of the sentence, it sounds something. So it has a one-to-one correspondence, so it has higher weight given this input. But if you take some middle word, let's say European Economic Area, and if you just see the spread of attention values, this single word depends on zone as well as European. And that's how the context is provided in each case. And building on this, then came something called as self-attention mechanism. So what they did was previously we just had RNN in the system. So this time they said, oh, why do we require RNN? We can just live without it. So this self-attention mechanism gets rid of the entire RNN part of the architecture. And this forms the basic building block of the transformer network. And the main thing or the main contrast with that of an RNN network is that RNN processes the sequence, a token at once, but here we process the entire sequence at once. So a high-level overview of the steps involved in a self-attention mechanism is that first we derive the attention weight, which is just a similarity score between the current input and all other inputs. And then after deriving the attention weights, we normalize the weights. And then we get the final attention weights after that. So I'll just provide the base architecture of the attention mechanism. So for example, if you're trying to find, if you have a sentence, say, with tokens as x1 till xt, and these are already embedded into a vector form, and we are trying to find a context of one of the tokens within this sentence, let's say that word is the xi. So we perform dot product of this word, which can be any of the word in the sentence, with every other sentence, just to understand where it sits in this sentence. Or we can say, what is the context of this word xi compared to the other words in the given sentence? And we calculate the dot product. And dot product, by its own means, gives you a sort of similarity between the two vectors. And then we pass on these dot products to a softmax value, and we get the attention weights of how much importance this current input plays in this current sentence. And we just grab all these attention weights together, multiply them with these tokens, with the input tokens, and then just accumulate them together, which we finally call as the context-aware embedding vector. So just to put it in a slight perspective, that we are just doing weighted average of input words x1 till xt, which we then get the word's context within the sentence. And yeah, and that's pretty much it. But the problem here is this is just a base level self-attention. If you observe, there are no trainable parameters within this. So the question is, where can we insert a trainable parameter, which is nothing but a weight matrix? Where can we add it? So literature defines that you call weight matrices as WQ, WK, and WV, and you just jot them with the current input token as well as the other tokens. And finally, you just have another weight matrix in the end, but I'll just explain each and everything. So these three weight matrices are usually called as the query key and value matrices for the tokens, for the respective tokens. So this usually comes from the fact that previously we used to have these database technologies which use the key value paradigm to store the data. So whenever we query a database, we obtain, it just matches with a certain key within the database, and we retrieve the key from the database. So the key can be a user ID and values can be the details. So you just query some user ID, it just matches it with a key, and it just returns you the values. So the important thing to observe here is that you can query multiple at once, allowing room for parallelization. And yeah, so a bit of a detailed perspective of how it works is, for example, if you're currently querying the second token, what is its context given this entire sentence? So we apply three weight matrices on the same token, the query matrix, the key matrix, and the value matrix, and we get three different vectors, Q2, K2, and V2. And we compare or perform a dot product with all other key values of the other tokens. And then we supply them to a softmax function. And in the end, we derive some attention weights. And these attention weights tells how much each token plays its role in the context of this current query token. And for this, the formula is just given as this. And if you just vectorize slash matricize, it's not a word, but yeah, the entire operation, you can see this familiar equation of QKV equals softmax of QK transpose over square root DK times the V matrix. And just to explain, the square root DK is just your scaling. It's called a scale dot product attention, where you just prevent the dot product to not reach higher values. So we just extend on it to as a multi-headed attention model. So we apply self-attention with multiple triplets of weight matrices. So instead of just having a single triplet of the query key and value matrices, now we generate lots and lots of weight matrices and just compare them in parallel. So each triplet indicates a separate head. So an interesting question here is, if you are defining a lot of weight matrices, does it increase the number of parameters or not? Anyways, so proceeding with the transformers. So now we have seen the basic building blocks of what an attention network is. And these blocks usually form the like a base block of the entire transformer network. So the transformer network is just composed of an encoder and decoder architecture. So the encoder just receives the input sentence and it passes it to the decoder along with some shifted outputs, which I'll discuss. So yeah, so for example, if you have this input sequence, so first you just calculate the embedding vectors and then you apply some positional encoding, which I'll discuss after this. And then you can see the encoder block consisting of the multi-headed attention as well as some normalization layers and MLPs and again a normalization layers. So this basically forms the encoder part of the transformer, and usually you can have multiple encoders within the network. Usually, if you take the original paper of Attention is All You Need, they had around 6 encoders, I believe. And so the main thing encoder does is that it is responsible for representation of the sentence. And now let's go to the decoder part. So the decoder takes, I mean, it's just everything is a simultaneous operation. That is, you give the entire input sequence at once, and along with it, you all, because this is like a seek-to-seek model, so you also give the start token, which is like the start of sentence token, along with the input sequence at the first point, and it just predicts the next token, and then you offer it the next predicted token along with the same input sequence, and it just predicts the next token again. So it just goes on until it predicts the end of sequence token. And the output usually gives the probability of each word in the dictionary, and we just pick the word with the highest probability and use that as the next predicted word. And coming to the positional encoding, so the thing is, if within a sentence, if you can have the same word multiple times repeated, the problem is that its context can change. So for instance, let's take a simple example as, let's take this English sentence which says like, bank left to the river bank while reaching the ATM bank. You have 3 words, bank, 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 but the context is different in the entire sentence. The word is the same, but it has 3 different meanings within the sentence. So you apply some positional encoding to the each bank word, such that it says if it is in this position, the context is different. If it is in this position, the context is different. And if it is in a different position, the context is a bit different. So usually we have a variety of positional encoding formulas, but the original ones include a sine and cosine positional encoding. So I'll just discuss about some well-known LLM models. So it all started with, say, the first GPT-1 model, which is the generative pre-trained transformer model. And this was introduced in 2018. So it just consisted of 110 million parameters, which now, if you compare, is like really less. And it involves a 2-step training process. One is generative pre-training, and the other is a discriminative fine-tuning, which we'll see in the next slide. So it was originally pre-trained on a book corpus dataset, and I believe it consisted of around 7,000 to 8,000 books. So yeah, so this is the architecture for the GPT-1. it just looks familiar to the decoder network of a transformer, which we have seen before. So the entire operation is same, but if you just see the output head, it has a text prediction as well as the task classifier. So the two outputs here indicate that the text prediction basically means it's just pre-training for the next word prediction. And then we have the task classifier. So we can have multiple fine-tuning or downstream tasks, which are usually shown on the right of the figure. So if you take the classification, it says takes in a start token and just gives it to the transformer network, and it just tries to classify what sort of text we are giving it. And then the entailment sort of classification means you have these logical statements where you have a premise, a hypothesis, and might just result in a true or false situation. And then you have text similarity fine-tuning, and then you have multiple choice question fine-tuning. And then comes GPT-2, which is 15 times larger than GPT-1, and it consists of 1.5 billion parameters. It is still the same sort of architecture, but it's trained on a bit larger data set, and it uses zero-shot transformers for instead of fine-tuning for downstream tasks. And the improvement over GPT-1 is that it has increased vocabulary and increased context size, that is the number of input tokens. And it is trained on a really large data set, which is the web text data set. And then comes the GPT-3. It is a similar architecture as GPT-2, but has a lot more layers and a lot more parameters and double the context size. And the token embedding for GPT-2 was 1024, and for GPT-3, I believe it's 2048. And in this case, since the network is like really large, the attention is replaced with the sparse variants. And it is trained on a multitude of data sets, which is web corpus, crawl data, Wikipedia, and book corpus. So a quick open question is evaluating LLMs across different sizes and capabilities. So how can we design fair and meaningful evaluation metrics to compare LLMs of different sizes and different architectures? And what strategies we could make such that LLMs are more accessible and practical for researchers who have like really limited computational resources? So anyone can feel free to answer.
Dear participants, you can unmute yourself. You can answer the question.
So anyways, moving on, there's another question as well. So if you're interested, you can answer it. So the question is just how can we determine the optimal level of fine-tuning required for a given task or data set? And could there be more thoughtfully designed pre-trained tasks such that we can reduce the need for extensive fine-tuning in downstream applications? So if anyone wants to answer that or discuss about it, please feel free to. So, okay, all right, moving on. So let's talk about the integration of LLMs with drug discovery. So in this case, I'm showing a specialized LLM. Specialized LLMs are trained very specifically to interpret domain-specific scientific languages like SMILES. If you see the input on the molecule here, which it has a notation. So there are several notations on how you can represent a molecule. So the most commonly used one is called as SMILES. So SMILES usually stand for simplified molecular, simplified molecular line entry system. Yeah, that's what it stands for. And it says how you encode your molecule, which you usually see as these kind of structures in the chemistry books or something. So anyway, so we have multiple encodings and we use to encode molecular structures, and some faster representations are used for protein, DNA, and RNA sequences. So these structured languages are crafted by the experts or scientists to encode the knowledge in a highly precise way, making them ideal for deep learning models and the other downstream processes. So in terms of drug discovery, So first thing is we need to understand the disease mechanism. So specialized LLMs can extract valuable genomic information from transcriptomic data, and this just enables tasks like transcription factor, binding site identification, or gene network analysis. And there are some models like ESM which are trained on protein sequences, and these are usually capable of predicting the structure and functions of proteins from their amino acid sequences, significantly advancing drug discovery. Someone has a question? So coming to the drug design, in the drug design phase, the models are trained in the SMILE system language, and we can plan some synthetic routes, predict reaction outcomes, and then design some new molecules which are tailored for specific properties like binding affinity. So this includes filtering out molecules with undesirable ADMET properties. So how do they work? So these models just act like tools. For instance, you can just input a protein sequence and ligand string, and the model just predicts a binding affinity score, guiding drug development decisions. And the main impact is that it just streamlines the entire labor-intensive process, and it offers a significant reduction in time and cost, saving the entire resources for the pipeline of drug discovery. And this is still while improving the accuracy. So let's for this presentation, we'll explore some 3 key applications of large language models in drug discovery. So we'll be focusing on areas where they have shown some significant potential to transform traditional workflows. So the first is the target identification and validation. So this involves using LLMs to analyze vast biological data sets, such as transcriptomic data or genomic sequences. And this is to identify and validate disease-associated targets. And these models can even assess a target's druggability to ensure it's suitable, if it is suitable for therapeutic intervention. And the second is the lead optimization and de novo drug design. So in the second application, LLMs help optimize the structure of lead compounds, improving their efficacy and safety profiles. Beyond that, they can generate entirely new molecules tailored to specific properties such as higher binding affinity or reduced toxicities. And finally, we can use LLMs for binding affinity predictions as well, which is to predict the interaction strength between drugs and their targets, such as protein ligand binding affinity, which is the usual case. And this capability accelerates the drug discovery pipeline by guiding experimental validation and prioritizing high potential candidates. So through these applications, what I want to say is that LLMs demonstrate the capabilities in tackling critical challenges across the different stages of the drug discovery. So I'll take a simple or a seminal paper, to be honest, on where it all started for LLMs for genomic data. So GeneFormer is a specialized large language model designed specifically for genomic data. So its backbone is a transformer architecture, which has been adapted to handle transcriptomic sequences instead of natural language. And it is trained on a gene corpus 30 million dataset, which is a really massive dataset consisting of 30 million single cell transcriptomes, allowing it to learn complex patterns in gene regulation and then predict the relationships between genes. So key feature is its use of masked gene modeling. So if you're aware of the BERT architecture, which is a bidirectional encoded representation transformer approach in language modeling. So this forces the model to predict missing genes based on the context and helping it understand the dependencies in gene networks. And yeah, so the GeneFormer's self-attention mechanism enables it to focus on regulatory hubs, identifying genes that are central to the usual disease pathways, and its fine-tuning capabilities also allow it to specialize further for disease-specific predictions, and which just makes it good for target identification. So a quick architecture overview is that it is built on a transformer network framework, obviously, and the input consists of gene expression matrices representing single cell data. So which is the model processes using its attention mechanism and feed forward layers. So the key feature of this architecture is its ability to selectively mask the genes, requiring the model to predict the missing information by understanding the relationships within the data. And this is the foundation of the masked gene modeling approach. And if you see the pre-trained workflow of this architecture, it is usually broken down into 3 steps. So first is the input gene expression matrix is fed into the model, then specific genes are masked, and which means the model cannot see the expression values. And finally, the transformer just predicts the masked genes based on surrounding context. And this is usually critical for telling/teaching the model to capture dependencies between the genes and effectively map the regulatory networks. So the impact of context-aware predictions in this case is that it allows the model to focus on key relationships within the gene network, which helps it to identify the central nodes or hubs that play significant roles in disease mechanism. And this pre-training equips the model with the ability to generalize across datasets. And this also means that it still remains adaptable to specific fine-tuning tasks for disease or experimental studies. So its primary strength lies in mapping gene regulatory networks, and by leveraging the attention model, it just identifies the central regulatory nodes and genes that are more likely to influence pathways and are actionable as drug targets. And the dosage sensitivity prediction is another critical application. So GeneFormer achieves an impressive 96% accuracy in identifying genes that play a significant role in disease progression. And this just enables the experts to focus on the most promising targets. And in silico deletion studies are a powerful use case. So here the model predicts the impact of removing specific genes, which helps the researchers hypothesize which genes to modulate for therapeutic outcomes before you can conduct some really extensive/expensive experiments. And the combination of mass gene modeling and multi-headed attention ensures GeneFormer captures some really intricate relationships that the existing methodologies might not do well enough. Yeah, so coming to another model, which is, oh, sorry. Yeah, sorry. Yeah, so let's just look at one of the case studies on how we can apply this on cardiomyopathy. So cardiomyopathy basically means a condition which affects the heart muscle function. So the model identifies a TEAT4 as a critical regulatory target using its internal mechanism, and it just prioritizes this gene as central to cardiac gene networks. And in silico deletion studies show that removing these TEAT4 improved the cardiac contraction, making it a strong candidate for therapeutic intervention. And these predictions were validated experimentally using iPSC-derived cardiac microtissues, demonstrating the GeneFormer's ability to connect computational insights with experimental validation. And the gist of this case study is that it just highlights how specialized LLMs like the GeneFormer can just bridge the gap between computational predictions and real-world experimental workflows, thus accelerating the drug discovery pipeline. So the next model is the ChemCrow, which is for the stage of lead optimization. In theory, it is used for everything, but yeah. So the figure just illustrates how the architecture of the ChemCrow, which is highlighting the integration of the GPT-4 with the chemistry-specific toolset. So the React framework usually allows the ChemCrow to reason through tasks step by step, and thus it makes it highly adaptable for complex workflows. And this entire system operates iteratively. For example, when tasked with designing a molecule, the model generates reasoning about the structure, uses a tool to propose modifications, observes the results, and updates its plan. So this loop ensures the model learns and improves dynamically. And how can we use this for de novo molecular design? So the model is tasked with designing, in this case, to design a novel chromophore molecule with specific absorption properties. So the workflow begins with generating some molecular structures guided by the model trained to predict properties like absorption wavelength. And these suggestions are iteratively refined. And it usually leverages the modified mode model in the backend and the property prediction tools. So in this example, the ChemCro model successfully designed a molecule with properties that closely match the experimental targets, demonstrating its ability to automate and accelerate the discovery of novel compounds, which are specific to the given targets. So how do we assess the metrics for the generated molecules? So it is important to evaluate their quality based on three key criteria. So first is the validity, and then uniqueness and novelty. So these metrics just ensure that the generated molecules are chemically valid, diverse, and innovative. So the validity measures how many generated molecules follow the chemical rules, such as correct bonding structure, and it also calculates the ratio of valid molecules to all the generated molecules. And this metric particularly is crucial because it directly influences how the model is being trained. And then comes the uniqueness property. And uniqueness just checks the diversity of generated molecules by evaluating how many generated molecules are unique among the entire valid molecule system. And usually a high uniqueness score indicates that the generator is exploring a wide chemical space. And the novelty metric evaluates how many of the generated molecules are new, meaning they don't appear in the training data set. And this is usually crucial for discovering truly novel drug candidates, such that it doesn't duplicate the existing molecules/drugs. So together, these metrics just ensure that the generated molecules are not just valid, but also diverse and innovative. And this is usually critical for, for efforts that you put in the drug discovery pipeline. So how can we use LLMs in drug target interactions? So one of the crucial steps in the drug discovery is how a drug interacts with its target protein. So LLMs are transforming this area by providing accurate predictions for binding sites, affinity strengths, and virtual screening workflows. And there are some specialized models like PROT-T5 and AlphaFold Multimorph, which focus on identifying the interaction sites for ligands on proteins. And these insights are usually invaluable for understanding the DTI, that is the drug target interaction, at a molecular level. And FOSFORMA model further improves the prediction accuracy by integrating sequence and structural data. And in the binding affinity prediction, it usually estimates how strongly a ligand binds to its target. So the existing models are like DocGPT, which usually excels in docking simulations, predicting how ligands orient and interact within the binding pocket. And the other model is a Psychic, on the other hand, and it simplifies the process by using only protein sequences and SMILE strings. And therefore, we just bypass the need for experimental 3D structures while delivering high accuracy. And how can we integrate into virtual screening? So the LLM models like the PROT-T5 and DocGPT generate protein embeddings that are used in molecular docking and the models which I was saying was about PROT-T5 and DocGPT. So they usually generate protein embeddings that are used in molecular docking and affinity prediction systems. So this integration accelerates the virtual screening process by helping the experts to identify high affinity candidates with minimal reliance on experimental data. So by combining these insights into binding sites, affinity strengths, and virtual screening workflows, LLM significantly enhance the efficiency of identifying promising drug candidates. So to conclude, how the transformative I mean, the entire drug discovery landscape has changed with the introduction of LLMs is that it just accelerates every sub stage of the drug discovery process, like the target identification, lead optimization, and the DTI prediction. And its ability to analyze complex data, generate some insights, and integrating with existing tools just reduces the costs and also while being highly efficient. So the main challenges currently are, though they bring immense potential, are the models fair enough? How are they scalable? And how are they accessible for researchers with limited resources? And further advancements in pre-training tasks, fine-tuning strategies, and model interpretability will further expand their applications. And to close it off, we integrate the LLMs with experimental workflows and create some synergistic systems that improve success rates across all stages of drug discovery, from right off from the disease mechanism to the clinical trials. Any questions?
I request the participants, please ask any questions if you have any doubts regarding this topic.
Just to iterate, the questions need not be about the bio itself. You can ask any of your LLM related questions, any deep learning models, any of your personal projects, it's fine. Yeah.
Participants here, you can unmute yourself and you can answer. You can ask any questions.
Sir, I have one question or two questions.
Yes, sir. Yes,
Sir,
sir.
Jack Roshan, sir, please.
Yeah, yes, sir.
Sir,
Yes.
can you please switch on your video, sir?
Yes.
Thank you, sir.
Sir, regarding while doing the drug discovery, the
Sir.
side effects of the drug is identified at the processing level or at the prediction level? That is
Usually,
yeah.
Yes, sir. So that's an interesting question because usually you can't predict what sort of side effects it can have in the beginning stages of the drug discovery itself, but usually this comes off during the clinical trials.
Okay.
Yeah. So usually we see these sort of side effects when we do with the, sorry. Yeah, so we usually see these sort of side effects during the animal trial process.
Okay. Okay. And whether I mean the one more question is protein and gene, and I mean apart from these two targets, do we have any other targets? I mean that can be done LLMs.
It depends, sir. In terms of drug discovery, these are the only two targets which we work on currently.
Okay.
Yeah. So because if you take any biological compound, it is just based on, it is composed of protein at the end of the day. And genes, what they do is just through transcription, they just convert the gene compound into a protein compound. So at the end of the day, you still have a protein in your hand. So yeah.
Okay. Thank you, sir.
Yeah. Thank you, sir.
Any questions, please? Now I request all the participants to switch on your cameras to click one photograph.
Feedback, madam. Ask any feedback.
I invite participants to give feedback in a few words also, please. Dear participants, please. I invite participants to give feedback in a few words, please. I'm requesting you. Can you please unmute yourself and you can give your feedback?
Yeah, hi, this is Dr. Pallavi Jain from
Thank you,
Galgotia's. Hi, this is Dr. Pallavi Jain from Galgotia's University, Greater Noida, India.
Hello, madam. Hello.
Hi, sir. That was very nice session and very very informative too. And basically,
Thank you, madam.
Related to the recent concept, okay, which we are studying since 3-4 days. So it was the true connection of that topic, LLMs, and he spoke very well. The speaker, Mr. Kaushik Bhargav, spoke very well, and I understood all the concepts very well, and that was a wonderful session. I can say it. Thank you. Thanks.
Thank you so much. Thank you.
So myself, Srinivas, sir.
Hello, sir. Hello.
Sir, it's very nice session, sir.
Thank you so much,
lot
sir.
of knowledge sharing has been happened here, and
Thank you,
you
sir.
explained the complex concepts in a way that was very clear and engaging,
Thank you, sir.
making
Thank
it
you.
easier for both people who already know the subject and people who doesn't know subject like me.
Thank
We
you.
all can easily follow your lecture, sir. It is very nice session, sir. Thank you.
Thank you so much, sir. Thank you so much.
Now I request all the participants, please switch on your videos. We'll take 2 to 3 photographs, please. I request all the participants, please switch on your videos.
Okay, done, madam.
Thank you, sir. Thank you, Rambabu, sir. So, on behalf of the entire organizing team, I would like to thank Mr. Kaushik Bhargav Sibangi for gracing us with his presence today. Your valuable insights and time have made a significant contribution to this event, sir. Thank you so much, sir. Thanks for joining.
Thank you, madam. Thank you.
Dear participants, we'll take short break. We'll take 10 minutes break. Later, we'll start session 2. After 10 minutes, we'll meet you again. Thank you.
Thank you, ma'am.
So we apologize for the delay. Our resource person will be joining us. Please wait 2 minutes. Okay. Welcome back, everyone. And we are now ready to begin session 2 of day 5 of our FDP on the revolution of large language models. Now, I want to give to the mic Miss Shweta ma'am to introduce our honorable guest of session 2, Shaurya Kushal Garu. Over to you, Miss Shweta ma'am.
Thank you, ma'am. Good evening, ladies and gentlemen. I'm Sweta Chikati, an assistant professor in the Department of Artificial Intelligence at Vidyajyoti Institute of Technology. It is my privilege and honor to introduce our esteemed guest, Mr. Shaurya Kuchal Garu. Shaurya Kuchal, the data scientist and visionary CEO and founder of Upsolve Solutions LLP, a pioneering AI startup headquartered in Mumbai. With an impressive 7 years of experience in building cutting edge AI solutions, he dedicated to empowering organizations to harness the transformative power of AI. At Upsolve, the focus is on driving innovation and enabling seamless AI adoption across industries. In April 2024, at the prestigious AI Day Mumbai, Shaurya Kuchal sir unveiled Auto Clarity, a proprietary enterprise AI platform. This groundbreaking platform has revolutionized processes such as creating detailed customer personas, automating form filling tasks, and streamlining call center audit reports, showcasing the potential of advanced AI in solving real world business challenges. I kindly invite Mr. Shaurya Kuchal sir to lead the processing of this session. Over to Mr. Shaurya Kuchal sir. Thank you.
Thank you, Professor. Um, Thank you for inviting me. Am I audible? And can you also
Yes,
please
sir.
confirm?
Yes, sir. It's audible.
Okay. I would want to start with a screen share. Can you allow me the permissions? Okay. Thank you. Professor, can you please confirm if my screen is visible?
Yes, it's visible, sir.
Okay. Thank you. So, in continuation with the previous session, we will today focus on improving methods of information extraction from not just limited data, but from potentially unlimited data size. The method that we'll be discussing today would be majorly focused on RAG pipelines. So, a major concern or a challenge that NLP has faced since the beginning is understanding the data corpus, understanding the user query, and responding in line with what the user is expecting. So document query as a step is defined in 4 parts. It is the ability of any model, Python code, or any code to understand a set of documents. These documents can vary from couple of pages to as big as in library or encyclopedia. The second part is because these documents are structured for human understanding, these are not directly formatted for computational efficiency. So there has to be a rearrangement of context to make it semantic grouping of the text. The third aspect is about understanding of a user query, retrieving from the set of documents which ones are the closest to the answer. Each document could have its own specific part of an answer. For example, if we talk about best legal advice, it depends on which state rules you are referring to or what domain of legal advice is required. So every set of document could have a penalty or an advice. So we need to find what are the relevant parts with respect to the user query and then reply with the correct answer. Now, the third step only retrieves the answer. It does not mean that it will also contain the correct answer. The fourth part of a document querying model or pipeline would ensure that the answer is in fact correct, has a reasoning back, and also it is very dense in terms of quality. It has less unwanted characters or fewer examples or concerns. So document querying as a process, as we'll go through in the slides that I will cover multiple times, this is a four-step process minimum. Each of these steps can further be divided into many more tasks. So before we start with the generative AI or how RAGs are being built, I would want to take a couple of minutes to also communicate how the entire flow has been built over the past few years or couple of decades. So as most of us would be aware, we have NLP algorithms which also which also attempt to achieve similar results. So cosine similarity, a very standard distance metric calculation, Euclidean distance. Both of these distances, cosine and Euclidean, are very common, efficient, and fast. The problem with both of them, so their approach is they work on word to word basis. They will parse a word to its root stem format and calculate the distance between different sentences or group of words. This could also mean it can start from single word to a multidimensional long word or n-grams. The next step that comes out as an answer is TF-IDF. Now the disadvantage of using cosine similarity or Euclidean distance is that it does not in no way communicate about a term or a word's presence in a document. So if a word fish is present in cooking recipe, the book, it could have similar, it could have cosine similarity very similar to that for a aquarium. Now, this does not mean that both of these are very important. In recipe book, fish could be one of the 100 recipes, whereas in aquarium or a definition for an aquarium, it could constitute a major part. So while these both of them would have very high similarity, the answer that NLP algorithm would give could lead to incorrect values. To solve this, researchers attempted to solve using TF-IDF as an approach. Now, TF-IDF stands for term frequency inverse document frequency, wherein just like the previous approaches, TF-IDF also calculates the frequency of a word in the given text corpus, but it also calculates the number of documents that contain this and essentially creates a score about how relevant a document contains a keyword. So this would avoid the mapping of fish in aquarium versus fish in recipe book, because in recipe book the TF-IDF score would be very less if it's a generic recipe book. But again, if I go for seafood recipe book, the TF-IDF scores for both the cases would be very high. And in that case, again, it could lead to wrong results, which is where we come and start with creating vectors. Now, word to vec is a very advanced form of vector. Before this, we also have one-hot encoding. So if we see in the slide also, if I write cosine similarity or similarity Euclidean distance or distance Euclidean, there is no significant difference between the two arrangements of words. One hot encoding does the same. So it essentially is a flag encoding which says in a size of n words vocabulary, how many words are present in the selected text, flagging them as 1 or 0. If present 1, else 0. This creates a long form matrix for each and every sentence. There are two key faults in the one-hot encoding approach. First, it requires a defined vocabulary. Anything beyond a vocabulary is always tagged as either a new word which goes one, so a lot of words could be tagged as new word, or it simply goes as 000. The second disadvantage is the output of one hot encoding contains, if it contains 10,000 words, which is a very small vocabulary, it could contain, for a sentence which has only 5 words, it could contain 5 ones and 9,995 zeros, which means that the content size is big, but the value in it is very big. So it is not a very, it is a very sparse matrix. To improve this, we have come up with two methods. One is word to vec, in which it is converting each and every word into a vector format and then creates the mapping. Using vector format, the advantage is the sparse matrix of one-hot encoding is eliminated. Similar algorithm is then extended at document level, which is mentioned as doc2vec. And instead of creating every sentence into a vector format, we convert every document into a vector format. Transformer is something that has completely revolutionized how NLP search algorithms or information retrieval systems work. Launched by Google in 2018 under the paper of first application, productive application was mentioned in BERT, which is bidirectional encoding retrieval transformers. These transformers, representation transformers, these transformers actually have very focused attention, capture the semantic meaning using word to vec or doc to vec. There is also another part of sentence to vec. There are character to vec. So vector algorithms can be extended at any granularity. And transformers have changed how we look at NLP problems. Before RAG started, there were many building pieces built by many different companies, independent researchers, and organizations, which have contributed significantly to the adoption of RAGs. So, RAG as a concept stands on 4 principles, as we have discussed. These 4 principles can also be mapped roughly to the 4 concept notes that I have shared on screen. So first, very important part of any information retrieval system would be the access of data. If we can access the data in structured format, it reduces the pipeline execution time, it reduces our efforts so that we can focus on development of the code. So document loaders, which are introduced by very standard libraries now. So I've kept uh, 2 samples on the screen on document loader. Document loader are the first part of any RAG pipeline. If we are using documents to query, if we are using text to query, then we can directly use text. But for large text, it is also recommended to use document loaders. So document loaders are basically provided to ensure that anything that comes out as a file system, it could be PDFs, it could be Word doc, it could be Excel, it could be CSV, text file, HTML file, web page, anything. We could parse the data into structured format and utilize it. So document loaders reduce our workload and we are able to directly use it. As you can see on screen, I've used snippets from LangChain. LangChain is a very popular library framework promoting development of LLMs and making the life of a generative AI developer very simple. As most of the building blocks are already available as a simple import statement, we can focus on development of the code. So using PyPDF loader, we can load out any Python, any PDF file. Using CSV loader, we can load any CSV file. There are also loaders available for web document, text files, Excel files also. And we are also free to use our own custom codes to build loaders for any custom file that might not have a predefined loader. LangChain community is also very active. If we provide any recommendation via GitHub, they are also active to include it into their documentation. Chat models. So RAG models, the difference. So document loaders all have always existed. They were not this organized. There were multiple variations in which document loaders existed. But this is not what has changed about the improvement in utilizing RAG versus traditional NLP. Chat models, for example, Llama, Mistral, Bedrock, Grok, Anthropic, or other models provided by Microsoft Azure on its platform or Gemini by Google. These models are essentially the brain of the RAG pipeline. Converting any document into a readable format, utilizing that document into how we can transform it, how we can load the data. This is the brain of RAG pipeline and is managed by chat models. Chat models are essentially LLMs, and they have been very helpful in parsing user query, parsing user documents, parsing the related mapping between the two, and generating a new answer. Most of the LLMs that we are seeing on screen also have the capability not just to retrieve a data, query a data, but also to generate its own phrased answer, not just taking out snippets from the document. Okay. Yeah. So we have discussed about document loader, which converts Python, which converts a PDF file into readable Python document, a readable Python stream of variable. Using chat models, we are able to understand it, query it, and perform our related tasks. Now, what was a major backlog of using vectors has been of using direct word to vec vectors has been solved in embedding. Embeddings reduce the data from indigestible or very huge amounts of data, humongous data, into small usable chunks of data, and plus also improve the structure in which it is organized. We split the data into multiple smaller chunks. Each chunk should ideally be a logical subpart. So if we have chunks which talk about how a certain manufacturing or assembly can be performed, then we should create separate chunks. Ideally, we should create separate chunks for separate parts, separate models, or separate fields at some logical interventions. There's also another condition. The smaller the chunk size, the less data the chat model has to deal at once, and the better its performance is. But the trade-off is it gives more and more chunks as an output. So the documentation, the parsing of output at a later stage becomes difficult. So documents can be thought of very large unstructured data. It could be thought of as string, and we have to reduce it into a more suitable format. Now, embeddings are essentially numeric outputs in some or the other form. And while they might look that it is not helpful, the embeddings directly contribute to the working of the RAG models, because embeddings are then succeeded by vector stores. And a vector store is a very important concept Vector store essentially adds a value to the just the embedding. So unlike word2 vectors or one-hot encoding or TF-IDF other models, where only a distance or a KPI or a value is calculated, or a representation of the information is stored with no semantic meaning altogether. Vectors also give a direction to it. So embeddings have numeric data, but when we store it into vector data forms, it gets a direction. And over here, a vector direction means that it has a meaning. So if we plot all our vector, all our embeddings into an n-dimensional space, we would see that words related to lunch, food, breakfast are heading towards one direction or are can be visually clubbed together, whereas the words such as sports, cricket, football would be heading towards a different direction and can be clubbed together. This is very different because this ensures that this limits my search space. So instead of searching for fish across all the occurrences, now I am searching for fish in the vector space where my queries also match. So vector stores are database options, which are like ChromaDB, Pinecone, Fez, and other. These are different from our standard traditional relational databases in the sense that they have inbuilt capability to allow similarity search and returning of those documents with intent. We have also discussed this slide in the previous session. So a RAG pipeline is what this looks like. We can ask a query, the query gets encoded via query encoder. The documents are already been encoded, split into chunks and encoded, available in the vector database and directly usable. Our query is then mapped on these documents part by part. Related parts from these documents are extracted. Once we see what these parts are, we get into the shortlisting of the information. We see what different parts of chunks have been returned. We run our AI model to see which one is more related to the query, mapping the scores, mapping the semantics, or using the fill in the blank method that was essentially trained on the chat model. So a chat model is trained using a very simple approach for our understanding. A fill in the blank approach, which says that dash is the capital of something or something is the capital of dash. So with this in line, the model has been trained a billion of times to give an understanding about what is being asked. If it is asked as the capital, then it returns New Delhi for India. If it is asked as the nation, then it returns India for New Delhi. Creating such models has enabled us to think how we can utilize their next word prediction or best word prediction to generate the answers. After related chunks have been extracted, these are again fed into the AI model. Again, I'm referring as AI model, but these are all the chat models that we have just seen. Between these chat models, the output is generated in the format or in the structure that we have requested it. If we say as a last step to translate this into Spanish or Hindi or Bengali or Telugu, it converts the it converts the output from English to Telugu in its best capacity. It need not be the correct answer. In the sense, it need not be syntactically correct in Telugu, but to the limitations in what chat model we are using, it will give the output. Okay, a very, very important next three slides. RAG model has 4 steps. This is slightly different from the ones that we have discussed already. Given a user query, this is very high level blocks. Given a user query, select the most relevant parts of the document. So most relevant parts of the document, this can be thought of as a simple way of finding a keyword in a PDF file using search function, or on websites when we do control F, or on PDFs when we do control F. So instead of returning just the presence of the word, it will return me the sentence which is which contains the keyword. The next part is, from these selected relevant parts, we have to pick the most relevant and contextually correct response. If a document works on cycles, motorcycles, four-wheelers, trucks, or other mode of communication, transportation, we have to select if the user was asking for the fastest way to commute between New Delhi and Paris, or between New Delhi and Agra. In that concept, we know that New Delhi to Paris cannot be done on cycle. So those parts have to be intelligently skipped. Now over here for step two, we are relying on the intelligence of chat models. But this is where the main difference is happening. Third part is validate if the selected response is correct. Now this is not essentially uh, present everywhere, but a lot of chat models and a standard pipeline of RAG also focuses on utilizing these models so that we can also try to see if the answer is correct or not. And the final output is rephrasing the response from the document to required crisp and structured answer. So if a document mentions long form answer because a keyword was mentioned in a passage 3 times or 4 times in a paragraph, we can reduce it and simply answer if we are looking for how was the performance of India in Olympics 2024. So instead of returning out that India was amongst the 190, 180 nations which participated in Olympics 2024, India participated in X, Y, and Z fields and had this much contingent strength and got these many medals, we can directly rephrase the response to give out crisp output such as these many were the gold medals, these are the silver, these are the bronze. Okay, now in the next two slides, which are also towards my last slides, we'll be discussing on step-by-step working process of this. And after this, I'll be open on any questions that might have arisen. So as a working process, we use embeddings. So information is now more organized. I've written this part from development perspective, from application perspective. So this might seem that a lot of information was already given, but we'll just go through this as a implementation perspective. So a lot of information is available. We convert it into smaller chunks. We then embed it. We then organize it because embeddings have logical blocks and we can query embeddings. Something similar to you, we can assume that instead of working on 100-page documents together, I have 100 monitors and each monitor is displaying 1 page at a time. So it gives me faster access of information at a substantially wide range. So instead of working on 1 page at a time, I am now able to scan through a lot of pages at a time. From those lot of pages, we combine into single page or 2 pages, 3 pages, depending upon the information retrieved, and then give out the answer. So we say that, okay, one second. So information seems numeric, that whatever embeddings we are seeing, we might see as it as a developer that, okay, earlier it was that India is the world's most populous or fastest growing economy. Now it might say some numbers, random numbers, which might seem gibberish, but the embedding models have been trained in a way that these communicate special meanings to the model, and using which it is able to retrieve the answers correct and fast. So food which could contain a list of burger, pizza, lunch, dinner combo meals is also related to fasting, wherein no food is being consumed. So these two would be close but not overlapping, but would still be closer than wood or electronics or TV. Next step is accepting the user query. So while we have converted our document into embedding format, we also convert our user query into embedding format. Only then we are able to do a vis-a-vis comparison and find the correct answer. This also helps us in reducing the search space. So the search vector space of the model, where we have to look for all the keywords, all the relevant snapshots where that keyword is mentioned. Now, because we are in the vector space, we try to find the matching vector. This focuses more on the meaning or the semantic understanding than on just the vectors. And yes, the next step is shortlisting all matching vectors. And a very important understanding is that while we are reducing, improving, standardizing the data, creating into embedding, each and every search query, user input query, would still match multiple vectors. There is no guarantee that it will match one vector. In fact, it is encouraged to have multiple vectors, because then we are also able to reason, shortlist, and select the most relevant answer. Okay, so the final slide on this is uh, converting a user query into the embeddings using vector search. So Pinecone, ChromaDB, both of them, and other vector source also have direct functionality now to allow us to query the database, vector database or vector store. They give us the list of outputs which we can communicate, saying that we want top 10, top K, top 5, anything. Those results are returned, and these results are then passed on to LLM for result generation. So in the expected format, so LLMs will convert, again, so LLMs, why we are doing this? We are doing this because LLMs have reduced context length. They, even the most advanced LLMs right now can go to only 2.3 lakh characters, tokens, which means that any document, any book, which is even more than 100 pages, will not fit into the LLM's context, and we will have to divide it into smaller parts. Dividing it into smaller part without using RAG can also work, but it is not going to be very efficient. It will not give direct results, because what is being observed in the research and in our application also, parts where the context is towards the meaningful answers are towards the end are being skipped. So LLMs cannot directly be used, but they are still very smart, the chat models. So we use them on the top of K results, the top K results. The next step is using LLM to create the output into the generated format. And then we can either directly consume it. If this is a chat application, we can push this out onto a display. If this is a long form application where a lot of other processing has to be done on top of the output, or a recursive mechanism is built, or in the chain that we had discussed earlier, self-stabilizing chain is a part, then we can utilize the RAG output to push the results back into the next LLM and trigger a new RAG pipeline stating this is the output. Can you verify if this is correct or not? Okay. So I have completed out my content quickly. Any questions that I can take up?
I invite participants to give feedback in a few words.
Participants, if you have any questions regarding this topic, please ask.
One minute, I'm going to unmute this. Okay, I'm going to.
Good evening, sir. Good evening, ma'am.
Yes, good evening, sir. Manoj, sir.
Good evening.
Sir,
Hello, switch on
can
your
you
videos and
Sir, Rajkumar, sir,
sir.
can you please switch on your video, sir? Thank you, sir.
is it visible?
Yes, yes, sir, it's visible.
Yes.
Sir, good evening, sir. Good evening, sir. Your presentation
Good evening,
is very
sir.
good, sir, and the clear idea we got, sir. Your wonderful presentation, sir. Thank you, sir. Thank you. Then
Thank
you
you,
are
sir.
take it as a process model. The last you are given the last two slides is very useful for sir. Depending on the where we can use for this application, all that, sir. Nice.
Thank you. Thank you, sir.
Thank you,
Thank
sir.
you.
Good evening, sir. Sir, can you elaborate that limit of tokenization at 2.3 lakh you have mentioned?
Yes.
That? What is the meaning that correct?
So LLMs work on the topic of token. One token is three tokens, three tokens roughly form 4 words. So a token can be thought of as a meaningful part of a word. It's not directly one word, but for our understanding, we can say 100 words take up 75 tokens, and each LLM. So LLMs are very tiny part of, can be thought of a very simple version of a brain, right? So a first standard child can only learn or remember 10 sentences, whereas everyone present on this call would be able to remember 20, 40, 30, 60 sentences. So this is basically our memory memory capacity. Tokens is also in a way how LLMs can retain the memory. So most LLMs right now in the market have 1.2 lakh. The bigger ones, the big LLMs have 1.2 lakh, 28 lakh tokens. Few LLMs have also come up which have gone to 2.3, 2.56 lakh. But the meaning of tokens is very close to word. So it is on the number of words that LLM can manage. So every character, special character is one token, unfortunately, but every word can reduce into smaller tokens.
Okay. Thank you, sir.
Thank you.
Sir, first of all, I'm Swarangi. Hello.
Hi, good afternoon, Sunangi.
Good afternoon, sir. First of
Good
all,
afternoon.
sir, your presentation were very nice, and the each and every concept, the way you delivered, it was very fantastic. Sir, my question to you is that how a single query can be matched to multiple vectors?
So if in a set of documents, it is so, okay, I'll just go this here. So a very interesting question. I might take 2 minutes to answer. So a single doc, leaving aside the query, a document can on a specific topic, for example, a document explaining how what Indian football team has achieved or cricket team has achieved in the past 10 years would speak about similar tournaments over and over. So a tournament happened in 2010, 2011, 12, 13, up till now. And there could be different team members. And when we query a anything. So, for example, if we query, a very good example would be in the Indian cricket team. Okay, so in the Indian cricket team, Dinesh Karthik has been in and out of the cricket team very frequently. So, if we ask what Dinesh Karthik has done, so it could answer he was a commentator, he was a cricket player, he was in the auction, he was not in the cricket team, so many things. But these are all related to him. So because first part of our query is what was Dinesh Karthik done in the past 10 years. So it will map these all answers. Then it will say if we add more specifics to our query as a part of Indian cricket team batter, then we'll get information related to batsmen, but that will also have multiple matches. So it is simple to think of the the vectors that we get as answer as a control F or a search mechanism that we do on PDFs, word pages, or websites.
Thank you so much, sir.
Thank you, ma'am.
Sir,
Yes. Good evening.
sir, one more question regarding, sir. You are given this RAG model. Suppose I'll be asking that query in pre-trainer. First, I'll given the write a Python program or create a Python program. Which one it will be we are getting the result, or both, or it will be same?
Sorry, can you please repeat your question?
Suppose I'll be asking a question. Write a Python program, addition of two numbers. Then create a Python program. What it will be the difference?
So RAG models will not be able to directly give out information which is not present in the context.
Okay.
If the documents that you have passed it as a document storage, if that contains basic Python programs or sample Python programs, so RAG models are for information retrieval and then parsing it. This is not for blank generation of the outputs. Yes, they can be used. Okay. So in your case, if you say if write a program, create a program, or generate a program, the output would more or less be same. But it depends on what chat model you're using. Secondly, as a phrase, creating a Python program would not probably yield this is the just a very hypothesis answer, but create a Python program is not a generic statement that we also write. We also always say write a code or generate a code. So that is expected to solve. But again, this is not a genuine factually correct answer.
Okay, sir. Thank you, sir.
Okay, thank you.
Anyone?
Sir, I have another question.
Yes, please.
This is regarding the context. I mean, from the vector store, we are able to get the embeddings. I mean, we are able to get the we are able to get the things. So in digitally, how the context is derived or how it is carry forwarded to till from the beginning to end. I mean, digitally, how from where it gets the retrieve the information. I mean, context to understand the context or to derive a context. I mean, from which database or which store it is referred.
So I'm trying to understand the question. Please correct me if I've understood this. The question is how the meaning of a document or of a vector is communicated throughout the layers and finally to the chat model. Is this the question?
No, sir. I mean, the context, the meaning is okay. The meaning is okay from the available store that it gets the things, and the context of the sentences.
Correct. So the context of the sentence is stored inside the embeddings. So, and the overall meaning of the embedding is stored as a vector, which is stored in a vector. So vector store can be imagined as vector databases. Embeddings will have the meanings of the sentence. Vector stores, vector database, vector will contain the overall direction or the context of the sentence. So if you can explain me with an example, I can try to answer better.
For a sentence, the meaning is derived from a store, from the store. Context for the sentence, the context of the sentence is derived from which store? That is my question.
So the context is not derived. So embedding is not a direct conversion of text into random numbers. Embedding also has embedding models. Okay, transformer models are used to convert and preserve the meaning or the context of the sentences into embedding format. So, and these embeddings form the vector when we store it into the vector database. So the context, meaning, both of these things are retained as a part of vector store. And when we query the vector store database, stating that this is the user query, find me the related top n keywords, we can also pass what mechanism of similarity we want to use. We can use cosine similarity, we can use Euclidean distance, we can use Levenshtein distance, we can use any other Hamming distance also. We can use any distance metrics while extracting the information. The retrieval part is managed by vector database. The storage part is managed, the information in storage part is managed by embedding models.
Okay, thank you, sir.
Thank you.
Still anyone, please? Can you please switch on your cameras? We'll take photographs. Dear participants, can you please switch on your cameras, please? 1 second, I'm allowing you 1 second. Now you can. Yes, just now I gave. Please switch on your videos.
Stop sharing the screen, madam.
1 second. Sir has to do.
Okay. Sorry. Yeah. Should I stop the screen share?
Yes, sir. We can stop.
Okay. 1 second.
Okay, thank you, madam.
Okay, sir, on behalf of entire organization team, thank for gracing us with his presence, sir. Thank you so much, sir. Thanks for accepting our invitation, and your presentation was nice. Thank you, sir. And one more participants, just small update for tomorrow's schedules. Tomorrow the FDP will takes place at starts at 2 p.m. to 8 p.m. 2 p.m. to 8 p.m. We have an exciting 3 resource persons followed by validatory ceremony will be there. Additionally, we are going to conduct one quiz and feedback. Everything is going to be shared in the Zoom link itself. Okay, we'll look forward to your active participation, participants. Okay, thank you. We'll see you tomorrow. Thank you. Have a nice day. Bye bye.